Hello everyone, we are from Group 3 and in this video we are going to present our dynamics project titled Vehicle Suspension System. My name is Dia Zakira, my metric number is 228098. Let's start with the introduction. So the study of vehicle suspension systems had been vital in automotive engineering for enhancing ride comfort, handling and safety. Serving as the link between wheels and chassis or the base frame of a car, so the suspension absorbs shocks and maintains tire contact. This project had focused on analyzing suspension dynamics, emphasizing how components behave under motion and load. The team had first developed a clear understanding of the system structure, then explored the impact of geometric factors, especially the instance center and installation ratio on performance. Tools like free body diagrams and CATIA models had supported the analysis of system response.
Hi, my name is Mama Azifah Mibe Shafi and my metric number is 228314. Okay, so for system description, the car spring is a key suspension part as it links the car's body to its wheel. The spring holds up the car's weight and soaks up road bumps. Spring stiffness controls how fast the spring pushes back and sets how fast the car's body moves up and down after a bump. The wheel speed makes the spring work. The spring reacts fast when the wheel moves fast, but if nothing else controls it, the spring will make the cars bounce wildly.
Assalamualaikum everyone, my name is Shazia Afika binti Muhammad Sawal, matrix number 227870. So for my part, I will be explaining about the assumption we make to help us understand better about the basic idea on how a spring behaves on suspension system. First, we assume that only the spring will react to movement. When the car wheel goes over the bump, the spring will compress, then it expands and pushing back to its original shape. It stores and releases energy with each motion and no other part is helping to slow or control this action. Second, the spring strength or stiffness is fixed. It means it always responds to the same way. A stiffer spring resists motion more, while the softer spring allow movement. But either way, its behavior doesn't change with different road conditions. Third, this leads to the continuous bouncing, where the spring pushback is often overshoot, making the car body move up and down repeatedly. The energy just keeps transferring between the wheel and the car. For my last point, the road bumps cause sudden movement. The spring will respond instantly, but nothing slows down the motion, so the bouncing will continue for a while.
Okay, hi, my name is Shanmugam and my number is 228431, and now we're going to do some parameter analysis of the suspension system. And first of all, we have to know about the instant center. This is the motion of the body is a rotation around this point. The position of the instant center point C is related to the chamber. Next is the jack force, which will cause the lift force under the base. So here is the simple draft of the chamber and tire, and here is the front view swing arm, which is very important when it's come to the suspension system. And then here is a simple draft of the suspension system, which only consider of the tire, the chamber, and also the spring. And here come the free body diagram, the coil spring and sprung mass free body diagram. Okay, here comes the important part, the equation of motion. Okay, when it's in equilibrium state, the net force in the y-axis is zero. So the weight of the sprung mass is equal to the force of the generated by the spring. And when it's come to the vertical motion by the tire, which is member, so we have the equation of the mass, second derivation of the displacement equals to the negative uh, steep constant of the spring and also the compression or compression of the spring. Next, here is the second relative displacement of spring. We have a relationship which is the compression of the spring is equals to the mass displacement minus with the pamper height. So we rearrange the equation in the relative motion, and we also get the equation of m second derivation of z minus the kz equals to negative mass second derivative of x, and is a ODE. So we solve the ODE to get the general solution. and we input the initial value into the general solution to get the final simplified general solution. And from there, from the final simplified general solution, we can get the relationship between the stiffness of the spring and to the relative motion displacement. And here is the graph we produce from the equation of motion to graph, which is coil spring mass system response to the base excitation bumper height, and also the relationship between the spring stiffness and relation motion displacement, which is called spring extension or compression.
My name is Alexander and Robert. My matrix number 228346. I will present about reflection. So from what we study, we learn a lot, which is we gain comprehensive understanding of vehicle dynamics, including stability, comfort, and contact. We learn about sprung versus unsprung mass. We learn about the coefficient of spring. We learn about the stiffness of spring. So from this study, we learn that it's developed the engineering skill by using the problem solving, modeling, critical analysis, and team collaboration. So for the challenges, we face to simplifying the complex dynamics, mathematical modeling complexity, and tool proficiency, which is using the CATIA to do our model. So for this study, we using the SDG 9, which is the industry innovation and infrastructure, which is aligned to building resilient infrastructure and fostering the innovation. So investigating advanced suspension system, especially double wishbone suspension. So from through the study, it's improved the understanding of safety, comfort, and handling the through engineering design. So here is the references. So here is the appendix 1. We have the orthographic view and double wishbone suspension model.
Okay, so for A2 analysis, it shows the different type of stiffness leading to a different displacement of the spring. We calculate the displacement based on Hooke's law, where the displacement is equals to force divided by its stiffness. Uh, we just assume the force is equal to 1,500 Newton on one wheel. As shown in the graph, the higher the stiffness, the smaller the displacement. And it also may reduce comfort of the passengers. That's it, and thank you everyone.